Hello, this is part 1 of lecture 4 of linear algebra, and this part is about basic properties of linear transformations. What are linear transformations? Linear transformations are functions from n-dimensional space to m-dimensional space that satisfy the following three conditions. So, first, zero vector is mapped to zero vector. Second, sum of two vectors is mapped to the image, sum of the images. And the third, if you take a vector x, if you scale it, that the scaled vector is mapped to the scaled image of the vector x. So again, if you have a function t from n-dimensional space to m-dimensional space, we say that t is a linear transformation if t of 0 is 0, if t of x plus y is t of x plus t of y, and t of lambda x is lambda times t of x for every x, y, and lambda. Lambda is a number, for x and y are vectors. Okay, three very explicit properties. Here's an example. You take plane, a two-dimensional space, and you have a function from plane to plane that take a vector x and reflect it in the x-axis. So basically, you can use a formula, vector x1, x2 is mapped to vector x2 minus x2, x1 minus x2. So you just change the sign of the second coordinate. Okay. Then this is a linear transformation. How to check this? Okay, you need to check these three properties. You take a zero vector, substitute here, and then using this formula, you see that zero vector is mapped to zero vector, 0, 0. Second, you take vectors x plus y. It has coordinate x1 plus y1, x2 plus y2. You substitute it here, and you get that t of x plus y is x1 plus y1 and minus x2 minus y2. But this is the same as sum of vectors t of x plus t of y. You have to use this formula twice. So this gives you second property. And third, you take vector x, you take any number lambda, you substitute here. You have a vector lambda x1, lambda x2. By this formula, t of lambda x is lambda x1 minus lambda x2. But this is the same as lambda times the vector x1 minus x2. So you prove that t of lambda x is lambda times t of x. Okay. So you checked these three properties accurately, and this proves that t is a linear transformation. Okay. You just have to check these three properties. Here's a more complicated example. You have a two-dimensional space and you have three-dimensional space, and you have a function from R2 to R3 given by this explicit formula. We claim it's a linear transformation. How to check this? Basically, you have to check three properties. That 0 goes to 0, you substitute here 0 vector, and you get 0 vector here. So first property is satisfied. Second, you take two vectors x and y in the plane, and you have to check that t of x plus y equals t of x plus t of y. Again, what you have to do, you have to substitute the coordinates of the vector x and vector y in the left-hand side of this long equality in the right-hand side, and you have to check that actually they're the same. You substitute, you play with vectors, and you check that this is the same as t of x plus t of y. This proves the second property of linear transformations. Finally, the third one, you take vector x and take some number lambda, and you have to check that t of lambda x is lambda times t of x. How to do this? Accurately, slowly, you take vector lambda x, its coordinate is lambda x1, lambda x2, you substitute it into this formula, you get this vector, but then you observe that this is the same as lambda times this vector, by one of the properties of vectors. If you have a vector, you can multiply it by a number, basically using this property. Yeah, but this is nothing that lambda times t of x. So we proved that t is a linear transformation. In some problems, you can be asked to check whether some function is a linear transformation or not. You basically have to check these three properties. Let me consider some functions that are not linear transformations. Here is one non-example. You take a map from the plane to the plane, given by this formula: x1, x2 is mapped to x1 square x2. Okay, here, this square should make us suspicious that this is not linear transformation. And of course it is not. Why? You have to produce counterexample. If a function is not a linear transformation, then one of the three properties in its definition is not satisfied. So you have to explicitly present a counterexample that shows that this property is not true for this function. Okay, here I just take a vector 1, 0 and take a number 2 and computed t of 2 times 1, 0. This is nothing but t of 2, 0, yet t of this vector. I substitute 2, 0 in this formula and I get this should be 4, 0. So function t maps vector 2, 0 to vector 4, 0. On the other hand, if I compute 2 times t of 1, 0 using this formula, I get vector 2, 0. So vector 2, 0 is different from vector 4, 0. So third property is not satisfied for this function t. So this is not a linear transformation. Again, just present a counterexample. Here's another non-example, which is a bit simpler. You have a function from the plane to the plane, which is given by this formula. And now you see this one here should make us suspicious. So clearly, no matter which vector we put here, we're not going to get zero vector, never. But it's better not to say this when you want to disprove that t is a linear transformation. It's better to present a counterexample. How? Just take vector 0, 0 and apply it to this formula. Apply this formula, and you see that 0, 0 goes to 1, 0, which is not zero vector. So first property of linear transformation is not satisfied. So this is not a linear transformation. Okay, so in many cases, it's useful, instead of checking three properties, check one, but more complicated. Okay, which is given by this criterion. So if you have a function from n-dimensional space to m-dimensional space, function t, this function is a linear transformation if and only if we have this equality for every real numbers lambda and mu and every vectors x and y. This is not hard to prove. The proof is in the lecture notes. I strongly suggest you to check the proof accurately by yourself. Try to prove it by yourself. This is not complicated. One way, it's basically you have to prove that if your function t satisfies this conditions of this lemma, that it's a linear transformation. You have to check that 0 goes to 0. You just substitute here lambda and mu to be 0, and you get 0 is indeed 0. First property is satisfied. To check the second property, it's enough to substitute lambda and mu to be 1. Then this equality becomes second property of linear transformation. And the third property of linear transformation, you just put mu 0, and then you have t of lambda x is lambda t of x, which is exactly third property of linear transformation. So this basically shows you one direction of this lemma. If you have a linear transformation that satisfies this condition, then if you have a function that satisfies this condition, then it's a linear transformation. Okay, good. We can apply this lemma in many cases. Sometimes it's handy because basically it's just one condition instead of three. But these three conditions of linear transformations are hidden inside this lemma. So basically this is roughly the same price to pay. Okay, here are some examples. More examples of linear transformations. Very famous linear transformation is called identity function. Identity function is a linear transformation. Why? Every vector, by definition, is mapped by identity transformation to itself. So vector x is always mapped to x by identity transformation, identity function. So if you basically want to apply this lemma, you have lambda x plus mu y. Of course, it's mapped to lambda x plus mu y by the identity function. So this proves that identity function is a linear transformation. And here's another example, very similar to what we considered on the second slide. You have a function from the plane to a line given by this formula. Vector x1, x2 is mapped to a number 3x1 minus 2x2. It is a linear transformation. Either you can apply this lemma, you just take this vector, lambda x plus mu y, substitute here, you get the formula in terms of coordinate of x and coordinate of y, then you play around with this and you check that this is lambda t of x plus mu t of y. This is basically follows from this formula. You see that this is linear transformation. Alternatively, if you don't like to apply this lemma, you can check that three properties of linear transformations are satisfied here. 0 goes to 0, sum goes to sum, and lambda x goes to lambda times t of x. Okay. And here's example, more complicated example of linear transformations, which we already implicitly considered in the previous lectures. This transformation is called orthogonal projection. First, let us define it as a function, and then we will see that this is orthogonal projection. It's a linear transformation. Okay, what is orthogonal projection? First, we take n-dimensional space, we fix some linear subspace there, and then we recall from lecture 2 that for every vector x in n-dimensional space, there are unique vectors v in our subspace V and vector w in its orthogonal complement, such that x is sum v plus w. So basically, every vector in n-dimensional space can be uniquely decomposed as a sum of a vector in the vector subspace V and a vector in its orthogonal complement. Okay, so this implies that basically for every vector x in n-dimensional space, there's unique vector v in V such that x minus v is orthogonal to all vectors in V. Yeah, so it's contained in its orthogonal complement. So here, vector x minus v is just vector w here. Okay, so we can define a map that maps x to this vector v. Okay, what is a function? It takes a vector and it uniquely corresponded to some output in another vector space. In this case, it's the same vector space. So we can take vector x and map it to vector v. Vector v is uniquely determined by x. Okay, so this means the function is well defined. So we can define a function usually denoted by PV. P stands for projection, and this V stands for this vector subspace V. So we remember where we project onto, and it's given by this. It's defined by this property. Vector x is mapped to vector PV of x, such that PV of x is in V, and x minus PV of x, it's contained an orthogonal complement to V. Okay, these two conditions uniquely determine PV of x by what we said earlier. So this vector PV of x is actually this vector V here. Yeah. Okay, so this condition defines us a function which we called orthogonal projection onto V, and here is a lemma. This function is a linear transformation. There are two ways to prove this lemma. One way, which is given in the lecture notes, basically you have to check that three properties of linear transformations are satisfied for this function. This is not complicated, but let's don't do this now. I strongly suggest you to prove this by yourself or read the proof in the lecture note. This is not very complicated, but you basically have to use these two properties, this and this. Yeah. Okay. So, for example, let me just explain how to prove the first property. You take zero vector, you have to prove that zero vector maps to zero vector. But look, if x is 0, you want to uniquely decompose it as v plus w, where v is in v and w is in orthogonal complement to v. But we can put v to be 0 and w to be 0. Clearly 0 equals 0 plus 0. And vector 0 is contained in v, and vector 0 is also contained in orthogonal complement to v. So we have this decomposition. We know it's unique. So this proves that vector 0 is mapped to vector 0. Yeah. So we proved first property of linear transformation. Okay. There is another proof of this lemma, which basically gonna follows from the formula, explicit formula for orthogonal projection, which we're gonna give on the next slide. This formula may look familiar to you because actually implicitly we already met her in lecture 2. Okay, let's take a look on this formula. This formula going to depend on a choice of bases in our linear subspace. Okay, let's fix a linear subspace of n-dimensional space, V. We fix some orthogonal bases of this linear subspace. We know it exists. There are many such bases, so we just fixed one of them. Okay, and then we have a nice formula for the orthogonal projection to V. Okay, for every vector x in Rn, PV of x is just given by this sum. Yeah, so this is sum of vectors Vi, basis in our orthonormal basis of linear subspace V, but multiplied by the dot products of x and Vi. Okay, we implicitly, we already proved that this is formula for orthogonal projection. We proved this implicitly in lecture 2. Okay. So now, if you use this formula, and if you use our criterion on which we discussed a little bit earlier, it's not hard to prove that orthogonal projection is actually a linear transformation. Yeah. So here, your vector x and here vector x, using the properties of dot product, you can prove this. This is not very complicated. This gives you the second proof of the lemma on the previous page. Yeah, I should stress that this actually explicit formula. If you know vectors v1, v2 up to vm, this formula gives you the formula for orthogonal projection in coordinates. So if you manage to find orthonormal basis of your subspace V, you can translate the sum in coordinates, yeah, and you get very explicit formula. Of course, it takes some time to find orthonormal basis of V, but once you found it, this formula can be used to find the explicit equation for the orthogonal projection, explicit formula. Okay, when n is small, we have very few cases for choice of linear subspace V. So depending on these cases, you may have different types of formulas. Yeah. So for example, for three-dimensional space, we can choose V to be 0 subspace, and then every vector is going to be mapped to 0 by orthogonal projection to V. Yeah, by definition basically, because PV of X is contained in V. If V is 0, this is always 0 for every vector. This is clearly linear transformation if all vectors are mapped to 0. The second case, when V is a line through the origin, are linear subspaces of R3. So then you have an orthogonal projection to a line, which is easy to visualize. And the third case, when V is a plane, and then a plane passing through the origin, and then we have projection to this plane. Again, this is easy to visualize. You take a point in the space, and you take a point in the plane, such that the vector joining these 2 points are orthogonal to the plane. Yeah. This is basically given this projection. And there's a final extreme case when V is the whole R3. In this case, orthogonal projection is just identity map. Yeah. And in this case, this formula becomes just the formula how to decompose vector X as a linear combination of the vectors of orthonormal basis of your linear subspace. And we already discussed this formula in the previous lecture. Yeah. Okay, so this is nice formula for orthogonal projection. You can use it if you asked to find explicitly a formula for some special orthogonal projection. There are other ways how to find a formula for orthogonal projections, which we're going to discuss in tutorials. Okay, now let me mention one very important properties of linear transformations. Basically, this property means that linear transformations are uniquely determined by the values on the basis of your n-dimensional space. Okay, let me be precise. So if you have a linear transformation T from n-dimensional space to m-dimensional space, you take a vector x in Rn, then you can decompose vector x as a linear combination of your standard basis vectors. So E1, E2 up to En are standard basis vectors of Rn. And basically x1, x2, and xn are coordinates of vector x. So when you put vector x as a column, x1, x2, up to xn, these are coordinates of vector x. But of course, you can write it down like this. Yeah. So now, if you apply t to x and use the property of linear transformations, so the sum goes to sum, and if you scale the vector, you can put scaling factor outside of your function. So you get this. So if you take t of x, this is going to be t of this vector, then it's going to be sum of t applied to x1, e1, plus t applied to x2, e2, plus blah, 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 up to t applied to xn, en. But then you put x1 outside of t, x2 outside of t, up to xn, and you get this equality. Again, this follows immediately from basic three defining properties of linear transformations. Yeah. So what does this line means? This line basically means that t of x is uniquely determined by coordinate of x and outputs of t of e1, t of e2, t of en, images of the vectors e1, en. So t is uniquely determined by this n vectors, t of e1, t of en. Okay, so if you know these n vectors, you know a formula for your linear transformation. Yeah, this is your formula. If you know this vector, if you know this vector, if you know this vector, then this gives you explicit formula. An important observation which we're going to prove, which we're going to prove and which we're going to use many times, that absolutely the same formula holds if you take any vector of any basis of your n-dimensional space. Namely, you choose any basis of your n-dimensional space, V1, Vn. It can be E1, En, it can be different. And then you fix some n vectors in m-dimensional space. And then this proposition tells you two things. So first of all, there exists linear transformation from Rn to Rm such that V1 is mapped to U1, V2 is mapped to U2, and Vn is mapped to Un by T. Yeah. And the second, that this linear transformation is unique. Again, so there's two properties here, two assertions, two results. First of all, that such linear transformation exists, and second, that it is unique. Okay, this is very handy. Yeah, in particular, we can apply this proposition to standard basis vectors of your n-dimensional space. Yeah. Okay, let us prove it slowly, but let us first prove uniqueness. Suppose we have two linear transformations from Rn to Rm. First is called T, second let us call it S, such that vectors of our basis V1, Vn are mapped by both of these transformation to the same vectors U1, Un. Yeah, you have this set of equalities. T of V1 is U1, and the S of V1 is U1. And similarly, T of V2 is U2, S of V2 is U2, and up to T of Vn is Un, S of Vn is Un. Okay, suppose we have this. We have to show that these two linear transformations are actually the same. How to do this? Two functions are the same if these functions apply to any vectors, give you the same result. Yeah, we have to take some vector x, arbitrary vector x in Rn. We have to apply t to this vector x, you get t of x, and you apply s to this vector x, you get s of x. We have to show that this is the same vector. Yeah, you take any vector x, we have to show that t of x equals to t of s of x. How to do this? We decompose x as a linear combination of our vectors v1, vn. We can do this. Why? Because v1, vn is a basis. Yeah. And now you apply linear transformation t to this vector and s simultaneously. Yeah. And what do you get? You get t of x using this criterion multiple times. You apply this criterion for the being linear transformation. So this t of x is going to be this linear combinations of t of v1, t of v2, t of vn. Yeah. Here you use the fact, in this equality, you use the fact that t is linear. Without being linear, this equality is not true. Yeah. Okay. But now, by assumption, this vector is this vector. And absolutely in the same way, when you apply transformation S to vector X, you get this sum. And again, by assumption, you get this sum. So these two vectors are the same. So this means that your linear transformations S and T are the same. If they're the same, when you apply them to this any vector in Rn, they are the same. Okay, so uniqueness is proved. And here, if you notice, we actually, in the proof of uniqueness, we use that we didn't actually use the fact that V1, Vn are basis, form a basis. We use the fact that they span Rn. And when we're going to prove existence, we're going to use, of course, the fact that they are basis. It's more delicate. Yeah. Okay, how to prove existence? So to prove existence, we need to basically show how to construct this linear transformation T. We construct it in this way. We take any vector x in Rn. We have to present the way how to construct T of x. We do it in this way. So first, we decompose X as a linear combinations of our vectors V1, Vn. Such representation of X is unique because V1, Vn is a basis. So here we crucially use condition that this is a basis. V1, Vn form a basis. So we can write down X as a linear combination of them in unique way. So there are unique numbers lambda 1, lambda n, such that X is this linear combination. And now we define T to be, T of X to be this vector. Lambda 1 u1 plus lambda 2 u2 plus blah, 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 lambda n u. So X is mapped by definition to this vector. So clearly, our condition of the proposition is satisfied. V1, if you substitute instead of X V1, you get V1 equal 1 times V1 plus 0 times V2 plus blah, 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 0 times Vn. So then, by this, our definition, V1 is mapped to 1 times U1 plus 0 times U2 plus 0 times blah, 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 Un, so which is nothing but U2. So V1 is mapped to U1, similarly, V2 is mapped to U2, and Vn mapped to Un. Okay, so this function which we just constructed, described, defined, this function clearly satisfies the initial condition of the proposition, but we have to check that this function is linear. Yeah, how to check that it's linear? Let us use criterion on the third slide, the criterion which we presented earlier. Yeah, we take two numbers, lambda in mu and r, we take any vectors x and y, and we have to show that t of lambda x plus mu y is lambda t of x plus mu times t of y. Yeah, we have to show this. How to do this? Basically using this definition, the way we define t, and the fact that sum of vectors is, has basic properties of sum of vectors. Yeah, let's do this. So we decompose first x as a linear combination of vectors v1, vn. Then you decompose vector y is a linear combination of vectors v1, vn. And what is t of x? It's a sum of lambda I ui. What is t of y? It's a sum of mu I ui. Yeah. And what is t of lambda x plus mu y? You add these two vectors, and then this is when you add them, you're going to get the sum of lambda I plus mu I times vi. So by our definition, this vector is mapped to this vector. Yeah. But then you use basic properties of vectors. That this is nothing but this. But this is by our definition lambda times tx plus mu times ty. Okay. So we proved that conditions of our criterion is satisfied. So this means that our map, our function t, which we defined in this line, is a linear transformation. Okay. So in the next part of the lecture, we'll consider applications of this proposition, which basically going to make a bridge between linear transformations and matrices, which we already implicitly mentioned several times in the lectures before and in tutorials. Okay, I'll stop the recording.